Okay, so I'd like to thank the organizers for the conference and for giving me an opportunity to speak. Also, thanks to all of you who chose to attend this session as opposed to the other sessions. Presenting work I've been doing with James Sully, as well as Lampros Lamprou and Sam McCandlish, who are totally amazing and outstanding postdocs at graduate students still at Stanford. So we'll be going from tensor networks to holography, and specifically from the MERA tensor network to holography. And I'm here to tell you that the way to go from one to the other takes us through an object which falls under the label of integral geometry, and that is the kinematic space. So probably we should start with a brief review of what tensor networks are. They're a tool in condensed matter theory, which is useful for efficiently representing many-body wave functions. And to explain that statement, I probably have to start drawing some tensor networks. So here's the most primitive tensor network, a vector. Why is it a vector? Well, in the tensor network language, every time I have a line, I imagine that this carries an index in some vector space, which and the dimensionality of that vector space we call the bond dimension. And every time I have a node, I have a tensor which carries as many indices as there are lines incident on it. So this is a vector. This is a tensor. When I connect lines, I form a trace. So connecting means tracing out. And now we're ready to make contact with the statement I made over here about many-body wave functions. This is a wave function. Why is this a wave function? Because when I actually write down the wave function on an n-body system in components, then the tensor of components is a tensor with n indices, and hence this structure over here. Of course, this wave function has exponentially many parameters in n, where n is the number of subsystems of this composite systems. So we can use tensor networks to simplify our life by giving this now amorphous tensor some additional internal structures, such as this one. For example, in going to this type of tensor network, I am now talking about an object whose number of parameters scales linearly and not exponentially with n. Of course, this type of network is not going to be, this class of states does not cover the whole Hilbert space, but that's just as well, because we're looking for an efficient representation. And obviously, an efficient representation cannot be good for every state in the system. The art, of course, in tensor networks is to define a class of tensor networks which have desired physical properties. So in my purposes today is to understand the holographic architecture of ADS3. And for that, I will use a special tensor network, which is what's called MERA, multi-scale entanglement renormalization ansatz, which was defined by Guifre Vidal in 2006. So I told you what tensor networks are in general. Now what's MERA in particular? It's this network over here. Because I'm interested in ADS3 and understanding a holographic representation of ADS3, I'm working in CFT2. And in this case, I have one spatial dimension in my system, and that's this dimension over here. How about the vertical dimension in MERA? The vertical dimension in MERA corresponds to scale. So the bottom layers correspond to the ultraviolet sector, while the top layers to the infrared sector of the system. The tensors which populate my network are unitary tensors which fall into two classes. I have what's called disentanglers, and their job in life is to remove UV entanglement as I go up. And I have isometries, and their job in life is to remove UV degrees of freedom as I go up. So we see that the structure of the network, as well as the types of tasks that these tensors are chosen to perform, tells me that this network is geared to implementing real space coarse graining of the wave function. Something I should say about the network is that it's a very successful variational ansatz for finding ground states of critical systems in 1+1 dimensions, for example, for the critical Ising model. So we know that in working with this network, I'm really describing the ground state, or perhaps not just the ground state of CFT2s. And finally, something that I will explain on the next slides, I haven't explained yet, is that this network manifests compression. Or for our purposes, what this means, or what this amounts to, is that entanglement entropies are apparent in this tensor network. So how does this come about? To understand this, I have to explain to you the so-called causal structure of MERA. It makes sense to think about the MERA tensor network as sustaining a causal structure. Why is that? Suppose that I want to compute the expectation value of some local operator O. So of course, I'm performing a trace of O and bra and ket of some state psi, for which I have drawn a tensor network for you. I have the ket here. The bra is going to be just the mirror image of that, and my operator sits over here. And now, the fact that these tensors are unitary is going to come to play. By forming a trace, so by connecting the indices over here, I discovered that I have a lot of cancellations. Every time I have a pair of disentanglers connected like this, they will just cancel out, form the identity. And likewise for isometries. So at the end of the day, I will have a cascade of cancellations in this, and in this region of the network, I get an object of this type. So the conclusion is that this expectation value only depends on a narrow subset of all tensors which enter this tensor network, and we will call this, this region the future of the insertion point of our operator. It's in this sense that MERA has a causal structure, and I should stress here that this is a causal structure in auxiliary time. So this is not the physical time of the 1 + 1 dimensional field theory, it's an auxiliary time which obviously corresponds to scale. Now that we know this causal structure, we're ready to discuss entanglement entropy. So we learned on the previous slide that thanks to this causal structure, only subsets of all tensors enter computations of expectation values. Suppose that I divide my system into two regions, A and A complement, and I want to compute the expectation value of an operator which acts non-trivially only on A complement. Then, as a corollary of the previous slide, I know right away that these tensors are going to be irrelevant for that computation. So this means that these tensors, yes, they do not affect expectation values of operators on AC. And another way to say this is that they form an isometry that acts entirely within HA. So if I just took this tensor network and contracted all the tensors up to this cut, that would be good enough for computing everything I want to know about A complement. Choosing or not choosing to contract these additional tensors just expresses my prepared state in a local basis, but it doesn't change the entanglement spectrum of the state. So a more highbrow way of saying this is that the state living on this cut is a compressed version of the state on A. And as soon as we say that, we have a bound on the entanglement entropy of the region A. If I want to compute the entanglement entropy, I can just look at this cut, and the most that it can be is just the number of lines that are bisected by this cut. Because if I wanted to maximize entanglement entropy, I would arrange for the state to be in product form, and every line would contribute additively to the entanglement entropy. Now, in this talk, I will make a stronger assumption. I will in fact assume that that I can estimate or compute the expectation value simply by counting the number of cuts. And the reason why I know that this, or the reason why this assumption is justified for my purposes, is that notice this reproduces the correct scaling of entanglement entropy. So the number of cuts I'm making over here grows logarithmically with the size of the system. So, well, yes, which is the correct scaling for entanglement entropy in 1 + 1 dimensions. And if you want me to discuss more about why this assumption is all right, specifically in the context of holographic theories, then please ask me after, like during the questions. Okay, so this was my lightning review of MERA, or what I want to tell you about it. Now, the title is going from MERA to holography. So I should give a review of holographic duality. But I have time constraints, and probably it's not necessary to review holographic duality at that level of detail. So instead, I just prepared a single slide, which gives us a sort of bird's eye perspective of what holographic duality is, or what it may appear to someone who is primarily interested in conformal field theory. So what is it? It's an auxiliary representation of a conformal field theory, which happens to involve gravity, and which manifests scale transformations with an additional dimension. That's the radial dimension in ADS. And furthermore, it manifests entanglement entropies in the form of space-like geodesics. This is the Ryuta-Kayanagi proposal. In general, I would be saying minimal surfaces here, but because I'm interested in ADS-free, it's just geodesics. But notice that these words could just apply just as well to MERA. The only real difference is that this additional dimension I just argued for you in the MERA case is time-like, whereas here in holography it is space-like. So we have a little bit of tension about this point, but other than that there is a striking parallel between the two descriptions. The MERA network is an object like this. Here's a spatial slice of a holographic geometry. Both have an additional dimension. In both cases, the additional dimension encodes RG transformations. And finally, entanglement entropies are represented by geodesics here by minimal cuts. But of course, minimal cuts are the natural discrete analog of what geodesics should be. So we have a very striking parallel. And it's this parallel that Brian Swingle advocated that we should study in detail in 2009 in a very influential paper. So my goal in this talk is to make this parallel quantitative. And the ingredients I will be using are the causal structure of MERA, what I reviewed for you earlier, the minimal cut prescription, so the fact that I can read off the entanglement entropy just by reading off the number of cuts made on the minimal cut. And my strategy for making a quantitative correction with holography will be to first construct a metric which captures all these properties of MERA. And then once we have a metric, we're going to ask how is it related to a holographic geometry. This metric is the kinematic metric, which Rob was kind enough to give you a preview of in his Tuesday talk. And that's what we'll be discussing today. So my strategy, find a metric which has these properties. I first start with the causal structure of MERA. And that's easy. If I have a causal structure, then I have null coordinates, and I know that my metric has to contain a factor du dv in these null coordinates. Let's talk a little more about what the significance of these null coordinates is, though. So suppose that I have a point which in this coordinate system has coordinates u comma v. What can I do with this point? I can drop a unique minimal cut from this point in the network. And then this minimal cut defines for me a unique interval in the field theory. And the coordinates of the endpoints of that interval are precisely u and v, the light-like coordinates of the point I started from. One way to say this is that this point over here, if it happens to be an isometry in the tensor network, is the final isometry which is necessary to compress the state of the interval u and v to bring it to the compressed form which lives over here. So this is what we have learned so far about the kinematic metric. It will have some conformal factor in front, but then it will have a du dv, which is fixed by the causal structure over here. Let's talk a little bit more about what the physical significance of the Lorentzian signature of this metric is. Suppose that I have consider a specific point in my kinematic space under construction, so a specific point in MERA with coordinates u and v. I want to ask now, in what way can another point in MERA, or another point in the kinematic space I'm constructing, be related to this point? Well, there are at least two qualitatively different ways in which they can be related. One is if I take a new point, also drop down a minimal cut and identify an interval that's associated with it, and then if I find that this interval is contained inside the interval I started from, I will call this time-like separation. A qualitatively different way in which a pair of points in kinematic space or a pair of tensors in MERA can be related is if the intervals that they define in the field theory do not, in fact, neither contains the other. So that's what we call space-like separation. Now, what is the crossover regime? What we would want to call null, not time-like and not space-like. What is the crossover regime between these two possibilities? Well, suppose that I want to take this time-like separated interval, the red one, and I want to bring it to the space-like separated regime. What would I do? I could take this v and push it over to the other side, and it will just become space-like when the red v hits the blue v. So the condition for null separation is if my two intervals have a common endpoint, either a common right endpoint, v equals v, or a common left endpoint, that's u equals u. And that's why u and v are null coordinates. So just to recap this, the past consists of intervals which are contained in my interval. The future consists of intervals which themselves contain my interval, and the space-like separated region is neither of the two. Okay, so we have the causal structure of the kinematic metric. Now we have to choose a conformal factor for it. So in order to do this, I invite you to consider a quantity called conditional mutual information. And that's this boxed quantity, a combination of 4 entanglement entropies. It depends on 3 intervals, A, B, and C, and I want you to consider the case where A, B, and C are contiguous, like so. So now with my minimal cut prescription, since I have a definition that involves entanglement entropies, I can just start drawing cuts that are going to compute this quantity for me. So I have 2 positive terms, and I forgot to say, so this is the quantity that appears on the left-hand side of the strong subadditivity inequality. And so strong subadditivity is the simple statement that this quantity, conditional mutual information, can never be negative. Okay, so So now I'm going to draw minimal cuts that correspond to the positive terms in the definition of conditional mutual information, and there they are. Now let me draw the cuts that correspond to the negative terms. There they are. And notice that I have plenty of cancellations. So this cancels, here and here I also have cancellations. So the only non-canceling contribution is going to come from just this region which I shaded over here. That's the place where my positive and negative counting cuts do not cancel out pairwise. And I will discover that conditional mutual information does nothing but, or is simply equal to, the number of isometries that live in this little causal diamond in MERA. Why is that? Because this quantity is equal to the number of lines entering from the bottom minus the number of lines leaving at the top. And when I perform that difference, I've only been going for 16 minutes. I timed myself. Yes, I was very particular about that. So, okay, so we have the number of cuts entering at the bottom minus the number of cuts leaving at the top. And the only way that I can have this quantity not cancel out completely is if I have an isometry living here, because isometries have the job of soaking up one of the lines coming from the bottom. And so this quantity, what it really does is simply counts the number of isometries in a little causal diamond in MERA. In retrospect, Strong's additivity of entropy is simply the statement that MERA never contains a negative number of isometries. That's all it was. Okay, so why are we talking about this? Because we need to choose the conformal factor for our kinematic metric under construction. And so here's a proposal. Let volume in this space count the number of isometries. So I'm going to say that if I have a little square of infinitesimal size du and dv in these coordinates, then I will want the volume of that space to be the number of isometries that live inside. Now, as soon as I said that the size of this little square is going to be du dv, I know what the coordinates of these points are. And now I can apply that to my definition of conditional mutual information, and I will discover that it becomes simply the second partial derivative of the entanglement entropy with respect to both endpoints. And this is the object that I will promote to be the volume form in my kinematics metric that I'm constructing. So this is the kinematic metric, and the first part of our strategy, constructing a metric that captures the structure of MERA, is now done. I have just a little remark to make. Notice that because I've equated volumes or areas of causal diamonds with conditional mutual informations, it imposes certain constraint. If I take a causal diamond and split it into two component causal diamonds, it should reduce to an equality between three conditional mutual informations, and I wrote it down for you here. Is it satisfied? The answer is emphatically yes. This is what's called the chain rule for conditional mutual information, and it's a well-known identity about conditional mutual informations, which follows directly from the definition. So in retrospect, the chain rule for conditional mutual information was really telling me all along, if you're going to look for a geometric interpretation in information theory, you'd better look for an additive quantity to correspond to conditional mutual informations, such as the area. Okay. So we have our conditional mutual information, our kinematic metric, and now the job is to map it to a holographic geometry. We have the metric, and well, yes, in mapping this metric, or in connecting this metric to a holographic geometry, the question I should really be asking is, how does, if I give you a point which has coordinates u and v, what does it really select? Well, it selects the following things. A unique minimal cut, which can be dropped from this point, and it selects an interval in the field theory, an interval of coordinates u comma v. So now, when I map this to holographic geometry, suppose that I do have, indeed, a holographic dual for a state of interest, then a point in kinematic space is going to correspond to this object. It fixes an interval, and it fixes an oriented geodesic. Why is it an oriented geodesic? Because if I just gave you a geodesic without orientation, you wouldn't know if I'm giving you this interval or the other interval. So it has to be an oriented geodesic. And so here is our conclusion, that the kinematic space, which we constructed over here, which has this metric, is the space of oriented geodesics, or the space of boundary intervals in a holographic geometry. Now that we know this, let's apply it to something. So here's the first statement. convex curves in the bulk of my geometry correspond to regions in kinematic space. Why is that? Well, take this curve, it's a convex curve, and suppose that I draw and I pass an axis through the bulk of my hyperbolic holographic geometry, and I look for all those geodesics which are bisected by this axis and which themselves intersect my curve of interest. Because every geodesic corresponds to a point, that gives me a bunch of points over here. In fact, it gives me a bunch of pairs of points because these geodesics are supposed to be oriented when I map them to the kinematic space. So each one geodesic contributes 2 points to this diagram. So I've done it for this axis, but I could also do it for this axis, and here it is, and this one, and this one. So far I have covered these geodesics, but then I can do this exercise for every single geodesic which intersects my curve, and I'll obtain an object like this. So it's in this sense that convex curves define kinematic regions in kinematic space. Now, this wouldn't be a very meaningful statement. I mean, it would be true, but trivial, if I couldn't attach a quantitative meaning to it. But it is very quantitative. The statement is that the length of this curve, in this case the circumference of the curve, is exactly equal to the volume of this region in kinematic space under the measure that we have defined on the previous slides. So in particular, because we constructed our measure from conditional mutual information, we discovered that the length of any curve in the bulk of ADS is really a combination of a bunch of conditional mutual informations. Or in the language of MERA, it simply counts the number of isometries in some region of MERA. Now, the title of the talk was From Tensor Networks to Kinematic Space, but here I did the reverse. I had a curve, and I went to tensor networks. I went to kinematic space. So let's go in reverse now. Suppose that I have a region in kinematic space, and I want to define a curve. This region, so this is a curve under construction now. If this region comprises geodesics that intersect my curve, then what's the boundary of that region? It's those curves which barely intersect the curve, i.e. the tangent curves. So every one of these points at the boundary of the region is going to correspond to one of these geodesics. The boundary is given by some function v of u, which has an interpretation that u and v of u, once I draw a geodesic connecting them, will be tangent to the curve I'm trying to construct. With this parametrization, I can actually compute this integral, and when I compute it, I get an object of this type, which those of you who followed that development will recognize as the differential entropy of this curve. So I'm now ready to say this really does reproduce the length of the curve. This is a little proof. But something is important about this proof. When I and my collaborators first came along and discovered this formula, we were just talking about pure ADS. But then Rob Myers and his collaborators came along and proved that this formula works for any holographic state or for any holographic geometry. And so the construction that we have done, the construction of kinematic space, is going to work regardless of symmetry for any geometry which obeys the Ryuta-Kayanagi proposal. I want to do a little example of what kinematic space tells us. Here's my little example. I have a geodesic here, and for that geodesic, I want to compute the length of this geodesic in the language of the kinematic space. So I have to find the volume of the region which comprises geodesics that actually intersect my geodesic. So what are they? Well, here's one of them, and that's a point. Here's another, that's a point. And there's a very easy condition for which geodesics are going to intersect my geodesic. I want one of the endpoints to fall within the interval, and the other endpoint to fall outside. So this is a region of this type. And now, okay, so that's the region. And if I integrate the volume of it, I'll find the length of this curve. I want to contrast this now with another curve which has the same endpoints, but which is not a geodesic. So what can we say about that? Well, every geodesic that intersects the orange curve clearly will also intersect the yellow curve. And so the kinematic volume corresponding to my orange geodesic curve is going to be strictly smaller than the kinematic volume corresponding to the yellow curve. And that's simply the statement that the orange curve is shorter. But I have more to say about this. There will be some set of geodesics which intersect only the yellow curve and not the orange one. And this will precisely account for the difference in these two kinematic volumes. So it will precisely account for the difference in lengths of the orange and yellow curve. So we have a geometric statement that to compute the difference in lengths of these two curves, I just have to identify the volume in kinematic space which corresponds to this class of geodesics, which intersect the yellow but not the orange. So I've drawn it for you here. And now when I refer back to MERA, I will discover that there will be a bunch of isometries living in this region. And from a MERA perspective, we have a very nice interpretation of the difference between lengths of curves which have the same endpoints. It's just a bunch of extra isometries that I would have to apply if I was doing an isometric embedding of a state that lives on this cut onto the state that lives on this lower cut, which is defined by the other curve. Okay, that's what I said over here. Here I have a statement about why the kinematic space of the vacuum, so for the hyperbolic plane, is de Sitter space. Rob kind of reviewed this in his talk on Tuesday, or reviewed this. So I probably can skip this slide now, since I'm running out of time. But let me wink at you and say, if you ask me a question, I can display this slide later. And here's the summary. I've told you about the quantitative connection between the MERA tensor network and the holographic geometry, which is mediated by integral geometry. I haven't really stressed this yet, but I've also given you a blueprint for constructing a tensor network for any holographic geometry. I'll just take the volume for this space, which it depends on entanglement entropies, so I can, if I know the entanglement entropies of all intervals, I can just define this space. Take the volume in this space and sprinkle isometries with the correct density, which is specified by this object. This is a blueprint for how I will construct a MERA-like tensor network for any geometry that obeys the Ryuta-Kayanagi proposal. My assumptions were, yes, the Ryuta-Kayanagi proposal, and also that in tensor networks I can compute entanglement entropies by counting cuts in MERA. And if I want this to be true, this imposes me, with reference to this blueprint for constructing a tensor network for a general state, this will impose some extra conditions that my disentanglers will have to satisfy. And I invite you to read our next paper when it finally comes up, where we will discuss why and how this will work. Here are some questions. I will display them in a moment, but for now, my thank you slide. Thank you very much.
Questions?
You volunteered, you're very particular, so let me ask you a very particular question that I've asked you many times before. You insist that this works in all geometries, but as you yourself have written papers, your construction works for some regions in most geometries, but not all regions. So isn't it inaccurate to claim that this construction is isomorphic to Ryuta-Kayanagi, because in general, your construction requires use of surfaces that don't compute entanglement entropy?
It's true that in the most general case, I will require the use of those, yes, but my attitude to this is different. So it's true that I can provably make statements of this type when that situation doesn't occur. But when that situation does occur, then I can continue to define my kinematic space not with respect to entanglement entropies, but with respect to geodesics which are longer, which do not compute entanglement entropies. And I would take the attitude here that perhaps we should think what would be a tensor network that would have that property, where some tensors would correspond to not compressing the state in order to reproduce the correct conditional mutual informations, but to reproduce the more general quantity, which we called entwinement, which involves longer geodesics.
So that quantity is not defined yet, but let me also add that the proof you mentioned by Rob and friends also only works with effective translational invariance, and Ryuta-Kayanagi doesn't talk about geodesics in general, but surfaces in higher dimensions.
I was very careful to say that I will be interested in the holographic geometry in free bulk dimensions, so I think we're okay here.
I mean, I'll just point out again that the statement you made was it works wherever Ryuta-Kayanagi works.
Yes. So this is a very good point, and I'm very grateful to Mukund for pointing this out. Definitely, this slide was intended to only work in ADS free CFT2, because that's all I was ever referring to. Yeah. Yes.
Yes. So I had a question about the causal structure that you talk about in MERA. So when I first heard about MERA, I mean, it was described as a way of understanding states at one time, right? And this was a sort of a scaling thing. So is it a convenience now to think of this as a causal structure, as you're clearly making good use of it and getting a two-dimensional de Sitter space and all of that, or is there something more?
Well,
when
this
you were
is yeah. So this is a good. So the causal structure, I don't know if it came off in my little review of MERA, but it's a consequence of working with unitary tensors, or populating my tensors with tensor network with unitary tensors. So this is really a question: are we buying anything by choosing to have our tensors be unitary? And I think the answer to that is yes. And the reason why I say that is that, well, not only am I able to make these statements, which otherwise I wouldn't be able to make, but also because if I ask questions, for example, under scaling, so what is the scaling superoperator in the tensor network? If I have an operator at some scale, what kind of operator does it become after coarse graining? Local operators will continue to be local operators in MERA only if I satisfy this unitarity constraint, and otherwise they won't. And so this is a nice statement about maintaining locality as I perform RG. Yeah. Maybe Gautam?
Yeah, so I have this question about, so in ADS3 we can make these large diffeomorphisms which reduce to conformal transformations in the boundary, and
yes.
Therefore you can change the vacuum state to some other state with some arbitrary stress tensor. So how is this reflected in your
Great.
way of...
Thank you very much for this question. So the answer is that it's not reflected at all. It's the kinematic space as I constructed it is a complete conformal invariant. And the reason why it's a complete conformal invariant is that if I start from the vacuum state and then perform a global diffeomorphism, a large diffeomorphism is what I wanted to say, that's tantamount to changing the cutoff on the boundary. And when I change the cutoff, notice that my entanglement entropy is going to change by an additive amount on the left endpoint and an additive amount on the right endpoint. So when I take the second partial derivative, the changes on the cutoff, both on the left and on the right, are just going to drop out from the second partial. So when I say that the Sitter space is the kinematic space for the vacuum, I automatically include all states obtained from the vacuum by large diffeomorphism.
Okay, let's thank the speaker now.
Thank you very much.